are here.
One more kind of. I'm just testing it out there.
Welcome and great to see you all here for tonight's lecture by John Anderson. A few things to let you know. This is the first Mission Aransas National Estuarine Research Reserve public lecture series of this year, this winter. There'll be several more coming up in January and February of next year. And this whole presentation was made possible by the very generous endowment provided by the Schweppe family. So this is part of the Laura Randall Schweppe Endowed Lecture Series in Marine Science. And this was made possible by a very generous donation in 1998 by Dr. Ewing Schweppe Jr. and his daughters Anne Ashmoon and Jane Scott, who provided this endowment for the Laura Randall Schweppe Endowed Lecture Series in Marine Science at the University of Texas Marine Science Institute. This series honors the memory of a wife and mother who had a lifelong love of the marine environment, especially around Port Aransas. And the award has since brought accomplished scientists to the Marine Science Institute to interact and foster collaborations with our faculties, staff, and students, and provide an interface between our institute and the general public. And there's been, over the years, around 50 speakers, and we're very, very happy, and it's my great honor to introduce Dr. John Anderson from Rice University. John is a Maurice Ewing Professor of Oceanography Emeritus from Rice, and he moved there in the 1970s, I believe in 1976 or 77, after completing an undergraduate degree at the University of South Alabama, a Master's of Science from the University of New Mexico, and then obtaining his PhD in 1972 from the Florida State University. He has had a very, very successful career with two major research pillars. The first one has been his research on the Antarctic ice sheet and the glacial response to climate change and sea level rise. And that has tremendously influenced the understanding of the distribution of the Antarctic ice sheet and has resulted in major changes in our view of the potential of the Antarctic ice sheet to melt in the future in response to climatic change. The other major pillar of his research has been around here concerning the evolution of the Gulf Coast, with a special focus on understanding past and predicting future coastal response to sea level rise and climate change. And our understanding of the changes that have happened here in terms of climate and geology over the past 10,000 years would be completely different if it hadn't been for John Anderson and his research group that has really changed our understanding in every regard. So his publication record is really impressive. He's published over 280 peer-reviewed publications and published 2 books, one on Antarctic marine geology and the other one on the formation and future of the Upper Texas coast. He's been an outstanding mentor with over 70 graduate students and was awarded several honors for that, including the Presidential Mentoring Award of Rice University in 2004. He's also been an Outstanding Educator Award of the Gulf Coast Association of Geological Societies. He received the Shepard Medal of the Society of Sedimentary Research in 2007, and more recently in 2019, the Doris Curtis Award of the Gulf Coast Geological Societies. He's also a Fellow of the Geological Society of America and the past president for the Society of Sedimentary Research. We are very, very honored and happy that you are here today to share your research with all of us in the room. Thank you.
Everybody hear me okay? Great. Thanks for coming. Honored to be here. And I have a long history with this lab. When we first came to Rice, I was asked to come and help teach a summer course here. And that was back in 1976 or so. And my wife Doris, who's sitting here, and our kids, back then, some of you may remember there was a houseboat where guests stayed, and we stayed on that houseboat. And my kids, who are now practically middle-aged, still remember staying on that houseboat. It was awesome. I think it sank. Just Tony Amos told me one time he came down to the lab and there was the boat. It had sunk. So, and I've had an opportunity to come back many times since. So the lecture today is really, it's a general lecture on what's happening to our coast. And I'm not going to confine myself to Texas, but since most of my work's been in Texas, and Texas seems to have some of the biggest problems, at least solvable problems. We always say in my group that Louisiana has the biggest coastal problems, but they can't solve them. They could have 50 years ago, though. That's the sad part. And they didn't listen to the science. And so they're now in a low position in Louisiana where they're losing most of their coast, their wetlands, and it's pretty much irreversible. So this is pretty serious business we're talking about here. Okay. I'm not getting how about if I use this, will that help? Nope. Well, it's not forwarding here. Yes, great, thank you. So my interests are in sea level rise and coastal response, but in this business, you start to broaden out quickly because we keep getting shot at from different directions. We like to think we're specialists and we look at sea level rise and how that affects the coast. And then we learn that, well, climate's having an effect too, especially here in Texas. And then we have subsidence to deal with. So climate change is a field where you constantly try to broaden out as best you can. This sort of shows what sea level's been doing for the last, for historical time. And when I first started in this business, there was a big debate going on while I was here at Rice during this period of time as to whether sea level was accelerating or not. Because back then the record was based on tide gauge records. That only the oldest one went back to 1900. So there was only 50, 60, 70 years of enough tide gauges around the Gulf of Mexico for some people to start to make the argument that the rate of sea level rise was actually increasing. And then we had satellites launched that were capable of measuring sea level rise from space. And this greatly improved the accuracy because we didn't have to deal with things like subsidence, for example. And that's the red line here. It actually shows real sea level since 1996, when the first satellite started collecting data. And as soon as those data were collected, people started saying, yes, there's an acceleration and it's real. In recent years, so we've seen it go from 1.4 millimeters to 6 inches per century, 12 inches per century. Now it's at, for the last 15 years or so, it's been at 39 inches per century. Now, when you do sea level, you get asked a lot by people. I used to get a lot of questions. People say, well, who cares about a 2 millimeter per year sea level rise? That's a 1/16 of an inch barely. Well, who cares are wetlands, because the wetlands that we're surrounded by here are, in order to survive, they have to vertically grow at the rate of sea level rise. Otherwise, they become rapidly flooding. So that's a battle that is literally fought at a few millimeters per year. And the battle is being lost by the wetlands now. And so this recent acceleration, this one here, is actually seems to be confined to the Gulf of Mexico. And so there have been people say, well, that's an oceanographic effect. It'll probably go away. Well, unfortunately, the impacts of sea level rise happen very quickly, and for the most part, they're not reversible. And so even though we've only been dealing with this really rapid increase, that increase is not reversible. And as we'll see, in order to go back in time to when sea level was rising as fast as it is today, we've got to go back about 8 to 9,000 years. So, and so this is just to emphasize that it's not just, the amount of meltwater that's going into the oceans. There's also oceanographic effects. And here in the Gulf, we get these the loop current that comes up into the Gulf through the Yucatan Straits, and then these eddies that spin off, and they're causing sea level to fluctuate as well. And reality is we don't really still have the right satellite observations to measure these things and see their impacts and things of that nature. So we're still learning as we go, which is kind of the story here. Now, this is, I know, a bit of a startling slide for you, but the source here, you notice, is NOAA, pretty reliable group of people. And this is from what's called the NOAA dashboard. And if you haven't seen it, I encourage you to just type it online, just go in and do a search engine, do a NOAA dashboard sea level. And it'll pull up a site where you can actually take the Gulf of Mexico, or you can take Mustang Island, Corpus Christi Bay, and you can raise sea level in 1 foot increments to see what happens. And this is what happens to the Gulf Coast in 30 years, 1950, with a 1 foot sea level rise. So what is that 1 foot? Well, when do we expect it? Well, this is how long it's taken for sea level to rise a foot without subsidence to rise a foot. So it took about 150 years for sea level rise that fast. It is expected to rise another foot by 2050. Whether it rises a foot or 2 foot or probably not much less than that is really dependent on greenhouse gas emissions. That's the only uncertainty. If we can curtail greenhouse gas emissions, we might get lucky and come out with this lower scenario. If we let things continue as we're doing right now, we'll end up with a scenario that's much worse. So we take that scenario, sort of the moderate level, the projection we're on now, meaning we continue with the similar rates of greenhouse gas emissions. Sea levels rises about 1 foot by the year 2050, and this is what the coast looks like. The areas in light blue are underwater. Now, years ago, you'd see figures like this, and they were based on what's called bathtub models, where you simply take the elevation, the landscape elevation, and you raise sea level and flood topography. You don't worry about subsidence, which varies. You don't worry about things like that. You don't worry about rates of wetlands accretion. So this NOAA model is much more sophisticated than that. They're actually inputting subsidence data that's available. They're looking at marsh accretion rates that vary across the region. And so it's fairly reliable, and I would argue it's about as reliable as we can get in the current situation. So it's not a good scenario. And so, oops, sorry. What's causing that rise? How could we account for something that's escalating and rising? Well, there are different ways to raise sea level. One's heat the oceans and they expand. That's very simple physics there. And if we look at what's been happening there, this is temperature in the Gulf of Mexico. And you can see that since this increase in sea level rise began, temperatures have been on the increase. I don't have in here the last year, which was the warmest year on record for Gulf of Mexico temperatures. So the oceans are heating up. This is this pattern sort of follows the global pattern. And so we're heating the oceans. If you talk to physicists who do modeling, they can actually say, well, the volumes of the oceans are this many cubic meters. If we heat that much water, sea level would rise this amount. It works out that's about the numbers you get. That, you know, this contribution in terms of millimeters per year. The other, and somewhat more disconcerting, is glacier melting. And this curve shows meltwater production by glaciers from 1970 to 2020. 2 years ago, my wife and I went to Glacier National Park. I had not been there in 30 years. I wanted to see those glaciers before they disappeared. And we saw them through binoculars. Last time we went 30 years ago, we could drive up and hike up to them. And so this is happening in real time. This past year, we went to Alaska, did the same thing. And again, this is happening at a rate that you can observe in your lifetime. However, the big 800-pound gorilla in the room are the ice sheets. The Antarctic ice sheet has enough ice that if melted, it would raise sea level about 200 feet. So Austin would be a coastal city. Now, that's not going to happen in a few hundred, maybe 100 million years or whatever. But the point here is that if we just remove about 0.1% or 0.5% of ice from Antarctica, that significantly affects sea level. Greenland, the same case. Now, Greenland's different because in Greenland, we can actually see the ice sheet melting. And this image is based on satellite imagery that shows in white here the sort of the current ice sheet, and then in light red and then dark red, land that's being exposed as the ice retreats, because the Greenland ice sheet is confined to land. So as it retreats, it's kind of easy to see. Antarctica is different because there the ice extends all the way out into the ocean. And most of the meltwater that's being produced under the ice sheet is flowing out under the ice sheet. It's not melting at the surface. And I've had people ask me, so, well, I've heard Antarctica is actually getting thicker. Well, maybe a centimeter a year thicker, but it's flowing faster. So if you do, you know, the math, it's losing mass quickly. And in reality, 30 years ago, I belonged to a group that studies ice melting, and we came together in this group to sort of formalize our collaboration, and we called ourselves EmeritusRice. And everybody's got to have an acronym nowadays. So NSF, the director or the guy at the NSF who was funding us says, that's a little bit too alarmist. So we renamed ourselves West Antarctic Ice Sheet Study or something like that. Now they're using terms in the literature like doomsday glacier to refer, and this is in scientific literature, to refer to Thwaites Glacier here. And there's enough water locked up in glacial, these two ice streams alone. And by the way, the areas shown in red here, these are parts of the ice sheet that are flowing very fast, much faster than ice can flow. So that means they're sliding. The ice is sliding across its bed, and most of the velocities due to sliding. And in places like these red areas here, these are called ice streams that are accelerating. They're flowing faster, but they're not getting thicker. So that means they're generating more water that's going into the oceans. And we can't measure that water. It's dispersed around the continent. It's coming out under an ice shelf 800 kilometers inland. So you can't go under there and measure that rate, but you know from the volume of ice that's being lost what's happening in terms of the contribution to sea level. And it's pretty dramatic. Okay, well, I'm going to talk a bit today. I'm going to focus a little bit on geological records of sea level rise, because we really, I think probably most of us in this room want to know, well, okay, we know sea level is going to maybe rise faster, but what's the impact going to be on the coast? And the problem is, we're trying to answer that question, is that climate change has sort of forced the Earth into a new condition, and it's happened so rapidly that we don't have historical analogs. Again, for sea level rise at the rate of the current day rate, we got to go back 8,000 years to when sea level was rising as fast as it is today. And so what was the impact of that rapid sea level rise? That means we got to go to the geological record to really understand that. And that's why we use these records, this case showing what's kind of the development of the East Texas coast for 11,000 years. Humans have been here that long. And they didn't really start affecting things until the last couple hundred years, but it's still an important contribution. Now, one question I get asked a lot is, how do we know that we're not simply reverting back into an interglacial? That this is just not the best time to be living. That you know, the Earth kind of goes in and out of these glacial interglacial cycles. How do we know that we're not simply experiencing that? And there's a good answer to that. If we look at this figure here, shows the it's an ice taken from an ice core in Antarctica, which can measure temperatures of the ice to within a few tenths of a degree Celsius. Pretty precise measurement. And what it shows is that as we go back from modern times back to 400,000 years, these temperature measurements are taken from ice bubbles that are frozen into the ice. So you can extract that 400,000 year air, and using the isotopic methods, you can actually measure Earth's temperature at that time. You can also measure CO2 and other greenhouse gases. And so if you look back, you see there's these cycles. So this would be an interglacial, and well, let's look at the sea level. This would be a high stand and sea level. It drops, it comes up, it drops. But the main points to make here is they're all pretty similar. These are following one another. So CO2 follows the same kind of cycle, roughly 100,000 year cycles, as does global temperatures, as do ice volumes. And that kind of makes sense because we know CO2 and atmospheric temperatures are pretty similar. If you increase CO2, you increase atmospheric temperatures. In fact, 30 years ago, people were saying, well, this is proof that we didn't cause the problem. It was going on 400,000 years ago. It's part of a natural cycle. That was the big argument that was put out by climate deniers. The problem with that argument is look at what CO2 has done in the last century. It's unprecedented now. And in fact, the disconcerting part is global temperatures and sea levels aren't as fast to catch up. And so we're still sort of catching up with what the global temperature record suggests is actually happening. And of course, we know CO2 is going to continue to drive things. Now, these large scale cycles are actually controlled by what's called astronomical cycles or Milankovitch cycles, which have to do with things like the orbit of the Earth around the sun, which is not constant. It expands and contracts, and it does it on 100,000 year time frequencies. So every 100,000 years, the distance between the Earth and the sun changes, and that results in changes in atmospheric temperatures. Every 40,000 years, the Earth is wobbling on its axis, which is controlling how much of the sun's radiation is reaching the poles. And that's another effect. And then there's this wobble effect that's called precession. So these are astronomical. You could set your astronomical watch to when the next glacial or interglacial will occur because it's astronomical. It's like sun going up and sun going down. But these do not explain that excursion that we're seeing happening in the last several decades. So we're not entering, just kind of coming out of a interglacial or glacial, or still, well, in this case, still entering an interglacial. Although there is something to be said for that, and that doesn't make me feel any better. It just means that we're still getting this long-term sea level rise that's being sort of exacerbated by these shorter term effects that we're talking about. So first thing we'll do is we'll take a look at what sea level's been doing we've talked about how it's changed over this longer time span. And one thing to note here is that if you look at where sea level was 120,000 years ago during the last interglacial, compared to where it is today, if you drive over to the little town of Ingleside, which is about 10 miles from here, you're standing on a beach. You can stand down the white sands, you can pick up seashells. You're 15 kilometers inland or whatever. You're standing on a beach, which is the 120,000 year shoreline. And that beach runs all the way from Padre Island, all the way up to into Louisiana and over into the Florida area. So that's a very prominent feature. It's called the Ingleside shoreline because it was first discovered here at this little town of Ingleside. And it's actually about 8 meters higher, 25 feet higher than the shoreline today. That's not very reassuring because that tells me if we're not truly into the interglacial yet, we've got another 25 feet of sea level to deal with before we're there. But not every glacial cycle, if we look back over those last 4 cycles, peaked at the same level. So we're sort of hoping that we are, in fact, have reached our true interglacial, but we don't really know that to be the case. But we do know that if it's going in any direction, it's still going up. It's not heading down at this point. Now, if we take that part of the curve and kind of blow it up, that's the time over interval over which our modern coast formed in Texas. And it's a complex coast. It's made up of estuaries and barrier islands and peninsulas and wetlands and very, very complex. If you think about the Gulf Coast as a whole, the Texas coast is more complicated than the rest of the Gulf Coast. Louisiana, they just worry kind of about marshlands and wetland accretion rates because that's their biggest problem. They're going to lose their barrier islands no matter what they do. Here in Texas, we have to worry about barrier islands and different kinds of barrier islands. We have to worry about different estuaries, types of estuaries, how they respond to sea level rise, wetlands. So we have a very diverse coastal environment, and those coastal systems respond differently to sea level rise and sediment supply, which is usually related to climate change. So we go back and we can reconstruct sea level. We can look for old coastal deposits and date them using radiocarbon ages. And from that information, we can actually construct a sea level curve that in this case goes back about 10,000 years. And it's a fairly precise curve. It's about plus or minus a meter, depending on where you are. And so what it's showing is that from about 10,000 years ago until about 8,000 years ago, sea level is rising as fast as it is today and faster at times. So again, this is our analog for the modern day. And you wouldn't have liked living on the Texas coast 9,000 years ago because the shoreline was retreating landward at anywhere from 20 to 50 feet per year at times. Wetlands, as we'll see, they were changing very dramatically. The estuaries were changing. And so this is the world we've forced ourselves into in just a matter of decades. So what was it like? You know, this is the question. And so and to understand that, we kind of need to look at that record. Now, we also have subsidence here in the Gulf Coast, which we have to be concerned about. And in generally, subsidence is about twice as high in Texas and Louisiana as it is over in Florida and Alabama. That's because we're adjacent to this big Gulf of Mexico basin, which is subsiding faster and has been for millions of years. And so our problems are bigger because we've got, you know, faster rates of subsidence to deal with. Okay, so back to the Mississippi Delta scenario. And so this is at, this is that slide that shows what the Mississippi, South Louisiana will look like in 30 years. We talk a lot, read a lot about the year 2100 and all the changes. And I always like to say, politicians find a lot of relief in that. Oh, that's 70 years away, you know. Reality is this is 30 years away. And that's why in my title on my side, I don't say the coast our grandchildren will live with. It's the coast so many of us will live with, or you will live with, and certainly your children will live with these changes. Now, has the Mississippi Delta eroded this fast in the past? Actually, no, it's grown in the past. Deltas are notorious. That's why they're deltas. They accumulate a lot of sediments. They grow. And so we have records that go back 5,000 years, fairly precise records of how the Mississippi Delta has grown, producing these big, huge lobes that extended out into the Gulf. So this is not nature taking its course. This is a reversal from what nature has been doing. We go further back in time, 100,000 years ago, this time here, we see that actually the Brazos River, the Colorado River, the Rio Grande River formed these big deltas. If you had driven from Alabama to here 100,000 years ago, it would have been like driving between New Orleans and Slidell. You'd have been driving through these, you know, marshlands with cypress swamps. That's what a lot of the coast is like. And the reason is because as we came out of the glaciations, there was a lot more humidity and precipitation. Rivers were delivering a lot more sediment to the oceans. And so typically throughout most of the past 120,000 years, the Gulf Coast has been characterized by growth of deltas and barrier islands and coastal features. It's only been in the last 20,000 years that that pattern has reversed itself. The other thing that kind of makes Texas unique is we have a climate problem here. And that is that we're sitting, if you look at the sort of the precipitation gradients for Texas, not much happens between Miami, Florida, and Mobile, Alabama, or for that matter, New Orleans in terms of precipitation. It's very humid, more than 60 centimeters per year kind of precipitation. And then you hit Texas and it starts to get really dry fast between Galveston Bay and South Padre Island. There's about 60 centimeters per year difference in the precipitation. And most coastal modelers will tell you that the greater the gradient of temperature and precipitation, the more dramatic the response to climate change. So Texas is expected to see the most dramatic climate change. And in fact, this is a model from our state climatologist showing what his model suggests is that the green here will continue to be fairly humid, but areas up in here in this part of Texas will get much more arid. If you look at the drainage basins for the Colorado River, the Brazos River, certainly the Rio Grande River, they all extend up into these areas that are going to see much drier conditions. And that equates into less sediment supply from rivers. So at the same time, sea levels rising faster, sediment supply is decreasing. And again, that's not a good scenario from a standpoint of vegetation. This just highlights what I was talking about earlier. These are sort of the precipitation gradients across the state. And you can see it doesn't really start to get dry till we get right here around Corpus. And it starts to get dry real fast by the time you hit the Rio Grande. So this is the area that most climate models are telling us are really going to shift, where we're going to see the most dramatic oscillations in climate. And that's the area, again, where if you look at the basins, the rivers that are contributing the sand or sediment to our coast, all of those basins extend up into this part of the country where we expect to see greater aridity and are seeing greater aridity. Here's a good example of that. This is the Colorado Brazos River Delta. It's just a simple Google image. And so here's the Brazos River and here's the Colorado, and you got this big kind of bulge that sticks out there. That's what's left of the Colorado Brazos Delta. that was much larger thousands of years ago, but it's now been reduced to sort of a coastal headlands. And it's flanked by Follett's Island and Matagorda Peninsula, which are two of the fastest eroding barrier islands on the Texas coast. That's kind of telling us that these rivers are not big sand producers. Now, there are ways to get at temperature records that go back farther in time to compare to our geological records. And one of the better ones is tree rings from trees. So you bore into a tree and you get these rings, dark light layers, and the width of those rings are a reflection of the growing season, which can be calibrated using trees from different areas to precipitation. And so there's actually a field of science of people that look at dendrochronology that do these kinds of things and reconstruct precipitation going back 200-300 years into the past. This shows a long-term record. It starts at 1,500 years and it goes up pretty close to modern day times. And we can see these cycles of times when these are droughts, these are flood periods prone to flood, and these are droughts. And so in Texas, and this is a record for West Texas, we're seeing these big swings that are operating over 30, 40 year type intervals. They're not really cyclic. They're 30 to 50, but little variability there, quite a bit. But they're showing some pretty major extremes. The decadal timescale suggests that these are tied to like El Nino, La Nina events, and they are, because a lot of our precipitation in Texas comes from the west, especially during the winter months. So if they're having a wet year in California, we're going to get a wet year in Texas, and that's all controlled by La Nina, El Nino events. So we're seeing some pretty big shifts here, but if we look at what's been happening in more recent time, and the dashed line here is actually not tree rings, that's actual measurements, meteorological measurements, temperature measurements that have been made over that. So what we're seeing is a dip down to, we aren't at the most extreme drought yet, but we're getting there. We're getting close. If we look at what the rivers have been doing during that time, this is the Rio Grande. Yeah, again, another big bulge in the shoreline where that delta hasn't been eroded back. This is the Rio Grande Delta in 1854. There was actually a delta there in 1854. This is the Rio Grande today. And you can literally wade along the beach across the Rio Grande without getting your waist deep. If we look at the timing of these changes, it corresponds to this onset of this drought. So again, sort of an example of where climate is starting to really play a more important role. So in general, we see is that if we go back to say 8,000, 9,000 years ago, sea level was dominating coastal processes and the evolution of bays and barrier islands for thousands of years during that time, as long as sea level was rising at these high rates. And then around 4,000 years ago, the sea level rise decreased significantly, lower than it is today. And at that time, climate started to pick up and dominate what's happening. In the last 20 years, we're starting to see sea level dominate again. And we think, again, that's because of this historical acceleration in the rate of sea level rise. One of my greatest concerns in terms of the Gulf Coast in this regard has to do with the bayhead deltas, like Nueces Delta. We're not far from Matagorda. Matagorda Bay used to have a big bayhead delta. It no longer does. Galveston, we have a delta in Galveston called the Trinity Delta. These deltas, based on that NOAA dashboard, are going to retreat landward on average between 6 and 10 kilometers during the next 30 years. That's amazingly fast. I mean, if you lived on the banks of the Nueces River in your lifetime, you would have observed that delta retreating significantly up the Nueces Valley. Mobile is the biggest one. It's actually because of the topography, and each valley has its own kind of topography. And the Mobile Delta here is going to actually retreat 30 kilometers in that same length of time. 30 kilometers, 10 kilometers per every 10 years, 6 miles. Sounds unrealistic, doesn't it? It just doesn't sound realistic that these deltas would retreat at those rates unless we look at the geological record. And what we see is that indeed these deltas have retreated in the past at rates that were even somewhat slower than the predicted rates, but in a similar amount. This is Galveston Bay, where we did a study some years ago. And when we do these studies, we collect cores from the bay and we collect seismic records. And I should just hold this. And so what we end up doing is we take a profile that goes up the valley. And this actually starts here at the coast at Bolivar Peninsula, and it goes up to the delta. And this is a cross section that starts at Bolivar Peninsula. It goes 30 miles to the north to up here on the Trinity Delta. And these colors here represent different coastal environments that the yellow is river, the green is bayhead delta, and the gray is open bay with oysters. And so what this is telling us is that over some period of time, in this case about 10,000 years, at that location, 10,000 years ago, the river was there, the Nueces, in this case, Trinity River. And then sea level went up and the river stepped landward, and that location became a bayhead delta. And a few thousand years later, there was another flooding event and the delta shifted northward again, and it became an open bay. So that's kind of what we're seeing in these NOAA projections. But in this case, it's happening, well, at rates. This particular flooding event here, where we can sort of go from the leading edge, the seaward edge of the Trinity Delta up to where it is, say, couple thousand years ago. That's works out to be about 6-7 kilometers per century or so. That's even slower than the NOAA projections, but it's at least telling us that these bays have experienced these kinds of dramatic changes. What the ecosystem impacts are from something like that, I certainly couldn't begin to tell you. There are hopefully people here that can tell us, are going to be worried about these things and starting to think about them, because these bayhead deltas, they are the anchors for the ecosystems within these estuaries. They're producing the nutrients. They're playing a key role in the estuaries ecosystems. And at this kind of change, what kind of changes are we going to see in the bay ecology? And the way to answer that question is go back and look at these cores, which fortunately we still have, and start to look at paleontological records of how the estuary adapted or how it was able to respond to those kinds of rapid changes. This is just an example of how dramatic we're talking about. That feature, this is a seismic section. That feature you're seeing there is actually a channel of the Trinity River, a distributor of the Trinity River. That's a subaerial feature. And then these more flat-lying sediments above it, those are bay sediments that have oyster shells in them. So that change right there, that what we call a flooding surface, at that location, it went from subaerial delta to open bay. And the radiocarbon ages that we have acquired from that location tell us that change occurred over 2 to 3 centuries. So again, these are the kinds of changes that we might be expecting in the future. Okay, well, mention a little bit about wetlands here in Texas, because I know there are people in this room that are interested in the wetlands. And our wetlands, again, are different from the ones in Florida and Alabama. And we see a lot more erosion due to wind erosion, especially in places like Matagorda Bay, West Bay, East Bay, where these northerly winds come along. They just pound the shorelines of these bays day after day and eroding our wetlands. That's, and to sort of illustrate that point, this is a photograph here from this part of East Matagorda Bay, which is kind of isolated and it doesn't get the wind fetch. So you still have the green here of the wetlands. There's pretty good fringing wetlands there still. But if you step over to this part of Matagorda Bay where you're facing the wind fetch that's much greater, much larger wave energy, this is what we see. Mostly sand flats, no wetlands. So the other problem we have is people would say, well, if you raise sea level and you flood the marshes, won't they just migrate inland to higher ground? And that's why nature would have it be. And that's what wetlands have done for thousands of years. The problem is, if you look at a Google image like this, that's a spoil bank of the intercoastal waterway. So the elevation suddenly goes from below sea level to 8 or 10 feet above sea level. And that intercoastal waterway extends all the way across to here. There's also that Ingleside barrier I told you about. That's a natural barrier. So it turns out that if you look at where wetlands can migrate, there's not as much ground for retreat of wetlands in Texas as we would like there to be, and certainly not enough to compensate for the rate of loss, which is very high. Okay, and then finally, I want to mention the coast, the beach, and what's happening yet. You've probably seen images like this. These are generated at the University of Texas Bureau of Economic Geology and by the group over here at the Hart Institute. And they show rates of shoreline migration over time intervals of decades where we have aerial photographs and charts to measure those rates. And if you look at the area, you see it's a lot of variability. It's not like every beach is eroding at the same rate. Some are actually growing and some are retreating, and some are retreating at 5 feet per year and some only a foot per year. Turns out Mustang Island here is the most robust island on the Texas coast. It's been around almost 9,000 years. It's hardly moved. That's good for Corpus Christi Bay because it's got a really substantial barrier that protects it. And so if we go up and down the coast, we see a lot of variability in the behavior of the barriers. Well, if we think that wetlands rates of retreat are fast, we can really see it better, I think, along the coast. This is off the seawall in Galveston, where there used to be a beach. And in fact, this is a photograph taken at the west end of that seawall in 1955. And you can see there was about 250 feet of beach. This is a photograph at that same location. And not only has that beach disappeared, but now it's eroded back a total of about 400 foot of erosion since 1950. That works out to about 5 feet per year. So if you see those numbers and you think those don't sound realistic, this is probably one of the better places to gauge how fast the shoreline's eroding. Now, again, if we want to look further back and say, well, have the shorelines eroded this fast in the past? Is this faster or slower than they've eroded in the past? We can do that again using geological tools. And so if we look out here off the coast, we've got these beautiful dunes and beach ridges that are out here. And if this beach started to prograde, if it started to grow seaward, these dunes would become ridges lined up in sort of single file to form what's called a beach ridge complex. If you look at Google images, certainly in Florida, you see beautiful examples of ridge systems that reflect progradation or growth. if the barrier doesn't, if it starts to get overwashed, then instead of having beach ridges form, you start to get washover deposits. And we can actually take cores and have taken cores from the shoreline out, and we can see pretty major differences in the types of sediments and the types of fossils that allow us to take a core and say, well, it got deeper or it got shallower. And then we can put that in this model like this. It says, well, this would show sort of shallow water shore face on top of deeper water shore face. So this kind of reflects growth of the beach. And in this case, we're seeing the marine muds starting to sort of move landward or on-lap the shore face. That's telling us the beach is starting to retreat. So we don't, the point here is we don't get always a good record of what shorelines are doing, especially if they're eroding, because you're eroding away the record. But if we go offshore, we can use this kind of a record to, where we can really see what that shoreline's been doing for thousands of years. And this is the sort of approach that we use. This is Galveston Island, that's been studied for over 60, 70 years now. Longest, probably best studied barrier island in the world. Here's those beach ridges. See how they line up, and radiocarbon ages from these cores tell us they're older back here and they're younger here. So that means the beach is growing. It's growing seaward. And we can actually, if we get ages, which that's what these are here, these are those same cores, that same core transect, we can calculate the rate of barrier growth. In the case of retreat, when the barrier starts to retreat, we can go offshore and collect cores that show us that marine on-lap, it's called. Again, using radiocarbon dates, we can tell how fast the system's stepping landward. So these are the kinds of studies we use to understand what coasts were doing for several thousand years. It's pretty accurate. It depends on how many radiocarbon dates we get, et cetera. But we talk in terms of, between 3,000 years ago and 1,600 years ago in Galveston Island, the beach was actually growing at a rate of 1 meter per year. In the last several thousand, before that, it was growing at about 0.5 meter per year. And then it turned around and started retreating landward. And now it's retreating landward at a rate of 1 to 2 meters per year. So that's a record of what the shoreline's been doing, that not just since charts and photographs have been available, but for the last several thousand years. And if we go up and down the coast, and by the way, the other thing that affects barriers are storms, and I haven't mentioned those. They're kind of noise in this geological study. And in the case, I get asked a lot by people, well, what's a megastorm? I mean, we use that term a lot, megastorms, and people say, what's a megastorm? And I'll say, a megastorm is a hurricane that we've never lived to see. And they have occurred. We see geomorphic features that reflect damage to the coast that is unprecedented in historical time. And one example is Bolivar Peninsula. Bolivar Peninsula 600 years ago was decapitated. Just completely took the top off the peninsula. There's a shale layer that is that layer right there that reflects that surface, and we can see it in every core we collect. So, and it's showing a period of time when you just, that red line, when you just decapitated the barrier. And then following that, you start forming new beach ridges again. So here they go, 600-year beach ridge out to the modern. It started prograding again. And it did that for a few hundred years. And then the modern sea level increase started, and it started stepping landward again. That's due to accelerated sea level rise. So there's some good records here of what these coasts have been doing through time. In Texas, we have some transgressive barriers, we call them. That's South Padre, Matagorda Peninsula, and Follett's Island. And what we mean by that is that those barrier islands are in the last phase of their life cycle. Islands are like people. They start out young, they take a lot of hits, They start to get mature, they're stable for a while, and then they start to get old. As they get older, they get lower and narrower, and eventually they can't keep up with sea level rise and they disappear. If you want to know what the coast would look like in that situation, just look at a Google image south of the Rio Grande, the Mexican coast, which is nothing more but sort of super tidal barriers that get overwashed every time there's a small storm practically. That's where our South Texas coast is heading at the current rate. Fallas Island is, so we have South Padre, we have, again, Matagorda Peninsula, Fallas. These barriers are eroding at rates of 2 meters per year, 6 feet per year on average. That sand is getting washed across the barrier. This is actually the North Mexican coast, what's called washover deposits. We can go ahead and take cores in those washover deposits and get the rate of accumulation of those washovers. And we know the rate of washover. We can, various ways we can calculate the amount of sand being brought in by longshore currents. And if the rate of washover is faster than the rate of longshore sand supply, we got a problem. That barrier has reached that point in its life cycle where it's now going to disappear, and it'll happen within decades. So that's the fate of South Padre, and that's, of course, that's going to affect Laguna Madre, just as, you know, in this case, it's going to affect Christmas Bay, some of these shallow bays, when these barriers start to become overwashed. We actually took a core in, well, one in Corpus Bay here and another one in Galveston Bay, and working with a palynologist who studies dinoflagellates, which is a tiny little animal, actually a tiny little plant, that is a good indicator of sea level. And what we found was that at the time that Bolivar Peninsula was decapitated 600 years ago, salinities in Galveston Bay jumped up to 30, 35 parts per thousand. That's equivalent to the offshore Gulf. That happened like that in the sedimentary record. It took 3 centuries for the salinities to sort of come back, meaning that the barrier required 3 centuries before it could build enough vertical height again, this barrier, to actually become a salinity barrier for that bay. So these things can happen fast, but they don't go away very fast. I'm coming to the end of that. If we take cores, we have a better record what the shoreline is doing offshore, because we don't have to worry about things getting eroded, building condos on these beach ridges, which is what's happening. All of Florida, we can't even use beach ridges because there's not many left, except in a few isolated areas. So we rely a lot on the offshore record. And what this shows is in yellow, this goes from, this image goes from Matagorda Inlet down to, this is Mustang Island, North Padre, and the yellow here represents barrier sands, and the blue represents sort of lower shore face, but still pretty sandy deposits. And you can see actually as you go along the coast, there's been a fair amount of variability in terms of when the island was advancing, when it was retreating. Turns out the reason that well, and you can see that this orange area, that's the Pleistocene surface. That's the old, the 100,000 year or more sediments. And that surface is by no means flat. It's got a lot of topography on it, which we call antecedent topography. So barriers like Mustang Island that sit in high areas, where there are low areas rather, where there's not that Pleistocene surface is very deep, you get much thicker barriers, and the thicker barriers are more robust barriers, because as the barrier is sort of being retreating, it's being cannibalized, it's feeding itself with sand. So a barrier island like Mustang is very stable, whereas a barrier island like Fallas Island, it's only 4 feet thick. You can take a post hole digger and dig through some of these transgressive barriers into the underlying Pleistocene muds. If we go up and down the Gulf Coast, we see that, and these are the locations where we've been able to do these kinds of shoreline migration reconstructions. We can see that in most areas, if we go back several thousand years, like Morgan Peninsula, Bolivar Peninsula, all of these beaches or these shorelines were advancing seaward for most of the last 4,000 years, and sea level rise started to slow down and level out. So again, it's kind of like the Mississippi Delta. It's eroding fast, but what's it been doing in the past? Well, there we know it was growing. Turns out the same holds true for the barrier islands up and down the Gulf Coast. Most of them have a history of growth, seaward growth, over the last several thousand years. And the red lines here represent the ones that are starting to retreat faster than a meter per year, which is most of them. So coming to the end here, as I promised. And so what are we doing? What are we doing about it? I always get asked, okay, well, you've painted this bleak picture. What's happening to our coast? What can we do? Well, one thing we can do is to get our head out of the sand, literally. No pun intended, I guess. But if we look at what's happening in Louisiana, for example, I always like to use the analog that Louisiana is in intensive care. They're going to die. They're going to lose their coast. They're going to lose most of their coast. There's nothing they can do to save it. Right now, they're making hard decisions about how much they can save. And we're talking about numbers of less than 20%. If they had listened to what the scientific community was saying 50 years ago and stopped dredging canals and building levees higher and doing some of the sediment diversion projects that were proposed, they wouldn't be in this shape, but they're back there in ICU. Here in Texas, we're sitting out in the waiting room. We're coughing like hell. And we don't know we're sick. We don't know we have a problem because our problem is more dispersed. It's not just about marsh inundation. It's about barrier island retreat that's increasing. It's about bayhead deltas that are starting to shift and migrate landward at very high rates. It's about wetlands that are being lost and have no place to migrate to. So we have our share of problems too. And just like in Louisiana, the politicians are not listening. And so if we look at an example of this would be this, each of the Gulf Coast states, as part of the BP settlement, was required to produce every 5 years a comprehensive coastal management plan. And sometimes that's a very elaborate plan, like in Louisiana. It's very thick. It's full of scientific tables. It's very science-based. Other times, like in Alabama, it's a lot of photographs and pretty pictures and words and not a lot of science. So it varies a lot as to what you can actually get away with and still get your share of the BP money. In Texas, we're a little better than most states, but we're far behind Louisiana. There is very little in the way of a integrated program in Texas where scientists from different disciplines are brought together here at the Institute, put in a room like this for several days and told, you come here at 8 o'clock in the morning, you leave at 5, and you eat lunch in the room because we got to solve this problem. And we're not going to leave until we solve it. That's the way science gets done. It's not the way we do it in Texas. In Texas, we started to distribute this money to different groups, and the progress is simply too slow to catch up with the rate of change. Remember, we're talking 30 years. Our coast will have dramatically changed. If you look at the 2019 report, and you can get this online, you won't find the term climate change. You will not see accelerated sea level rise. And if you flip back to the bibliography, the references, you'll find of maybe 80 or 90 references, 5 peer-reviewed scientific papers, compared to Louisiana, where it would be 250, 300 scientific papers. And so what are we doing to solve our problem? Well, Not a lot. I'm sorry. I wish I could be more positive. And I know I probably have people at GLO that are listening to me right now, and they're going to, tell me about their discontent with what I've got to say. And if they want to debate, we've got the evidence right here. Now, they caught some heat at the GLO for kind of blowing off sea level rise and climate change. And so they kind of produced an add-on report a year ago. And this one actually mentions sea level rise and climate change. It's in bits and pieces, but it's there. My problem with this report is it deals with changes that will occur by the year 2100. If I'm talking to a politician and I tell them, oh, these changes will happen in 2100, that's about like saying, if I'm a doctor and I say, you've got cancer, but you got 40 years to live and you're 80 years old. So that's about the same effect. I mean, you're not going to have much impact. There's a big difference between 2050 and 2100. And by 2050, most of the damage is done. So we find ourselves in the same situation as Louisiana because we're just headed merrily down that road. Now, one example of what Texas is doing in terms of how we're spending our money, this is the Ike Dike. I don't know how many of you are familiar with the Ike Dike, but that was after Hurricane Ike. Somebody came up with the idea that said, well, we'll just build a bigger seawall. It'll be higher and it'll be longer. It'll go all the way to one end of Follett's Island, all the way to Bolivar Peninsula. And we'll build a beach out there 200 feet from the current beach. Hell, we can't nourish our current beaches, and we're going to add 200 feet to them. And so, and this plan has caught a lot of flack from mostly, citizens. And so it's changed, but there's the Ike Dike. It used to run across Follett's. They gave that one up because they finally said, yeah, that would be a waste of money. But I plotted that on top of what the 2030, 2050 map actually looks like. So by then, this will all be bay. So what are you trying to save here? And the other thing that bothers me is that by the Corps' own calculations, it's going to take 39 million cubic yards of sand to put that beach out there. You know how many truckloads of sand that is? I mean, we're talking about millions of dump trucks here. And we don't have a lot of sand. If you go offshore here, it's mud. It's the Texas mud blanket. We have a name for it. So where's that sand coming from? That's going to, and here it's actually 250 feet. Well, they don't know. The reality is, when you go to the meetings, and I've gone to the meetings and talk to the Corps, and you say, where are you going to get that sand? Well, we're looking for it. Okay, well, you need that's a pretty major body of sand here. By now, we should have found it with the cores we've collected. And we answer that question, and I'll do that in a minute, but I wanted to say one more thing before I do as to where we can find the sand. The cost of Ike Dike is about $30 billion, although I hear now it's gone up about 10 billion. That just kind of happens overnight. You kind of learn, oh, it's now up to 40 billion. Haven't you heard? That represents 84% of the funds that Texas has for beach restaurant, for protecting our entire coast from the prairie land out into the Gulf. So 84% of the available funds for coastal protection in Texas will go into one dike, one hard structure, for which they can't even demonstrate where they're going to get the materials to nourish those beaches and to build that structure. So this is where we're at in Texas. And I think we're obviously going to have to get more serious. Now, are there things we can do? I talked about those big deltas, and I had motive there, and that's because those deltas have associated with them sand bodies. And when we've calculated the volumes of sand there, we're talking about, the same kinds of numbers, 30 million or so cubic meters of sand. probably more than that. That's a conservative estimate. So the sand is there. Don't give up hope. There's a lot of sand out there. We've mapped those sand bodies. We need to do a lot more sampling them and looking at the quality of the sand, things like that. But that needs to be happening right now because the nourishment projects are going to have to start in a decade or so. And then we got to get hopper dredges that can, I think personally, people ask me what to do. I said, Texas ought to just buy them a hopper dredge. The hell with the Corps of Engineers. We're a rich state. We can buy our own hopper dredge. We just let it go 365 days a year, going out there and getting sand, bringing it in, putting it on our beaches. And I think that's probably what's going to have to get done. It may not be the right solution, but this seismic data is just to show that there's that Texas mud blanket. There's that sand. It's under 150 feet of mud. But there are places which are shown here where it comes to the surface. We already have that data. We collected it 30 years ago, 20 years ago. So we know where the sand's at. We know it's a lot of sand, but we're going to have to get moving here. And right now, I'm afraid we're not moving as fast as we probably should be. Well, I'll let you just read these conclusions. And I wanted to say that if you're having maybe concerns about some of the science behind what I've been talking about, we have a book out. It's published. It's a memoir published by the Geological Society of America. So it's a peer-reviewed publication. It's available for download free of charge. So you can go onto the Geological Society of America website, bookstore, and type in Anderson et al. 2022, and it'll take you to this. And then there's you got to look a little bit because they don't like you to get it for free. It's a lot faster if you pay the $39, but hang in there for another 60 seconds and you'll figure out how to get it free. And then the last thing I wanted to mention was that one of the reasons I was looking forward to this talk is because I've written a book, and I've written the book for this audience. And so you can see it's a pretty risque title. The demise was actually called Gulf of Mexico Demise, which I think I maybe convinced you is not an unrealistic title. And so this should be out about this time next year. So keep an eye out for it. I try to use a lot of scientific figures, documentation. I didn't get this off the web. I didn't get this off of social media. It's science-based. And so this is what I've been trying to do to kind of get people alerted to this situation. I think everybody in this room can play a role if you talk to people and you try to advertise the fact that we're having problems here, and the people in Austin are dragging their heels in solving those problems. So I'll stop there and I appreciate your time. Thank you.
Questions from the audience?
This is where I switch.
Right away, like stop dredging, which is what it sounds like has been the demise of the Louisiana coast.
Well, again, our problem is different, but certainly, thank you. I'm sorry, I forgot about their outside listeners. Yeah, the question is there something we can do now? And I think that we're struggling right now in Texas to find enough sand to nourish beaches, the ones that are disappearing, let alone growing them 250 feet. So sooner or later, we got to put a bunch of scientists in the room who have actually worked out there and say, okay, if you got some sand and it's over 1 million square kilometers, now's the time to show us the data. We can do that tomorrow morning if people want to come and do that. But so that's one thing we can do. We can start to face the people who are actually dragging their feet on this issue. Not so much. I mean, dredging causes a lot of problems. And as I mentioned, the intercoastal waterway has a ridge, the Treadspoil Ridge, that runs almost half the distance along the Texas coast. And that's stopping the grasslands and the wetlands from migrating landward. So that's as far as they can go. I mean, they'll work their way around it, but that's going to be certainly seagrasses. That'll be the end of the seagrasses when they reach that barrier. And then dredging operations, like when the Corps dredges channels, things of that nature. I mean, there you're getting into this big argument about the economic importance of the Houston Ship Channel, these ship channels, and is the damage outweighing, the environmental concerns? That's sort of something you have to do with a bunch of economists in the room, unfortunately, maybe, but just the way it works out. My personal feeling is that dredging is not the worst, not by far the worst of our problems. That it is having its impact, but our challenges are sea level rise and climate. These rivers are not delivering near as much sediment to the coast as they were 1,000 years ago, 500 years ago. And some of that's natural climate variability, as I showed you, but some of it, but we're exacerbating that problem. So, sorry if that's a dodge.
Okay.
Yeah, go ahead. Oh, okay.
What impact is the damming of Texas rivers and water use having on wetlands nourishment?
What's the last one?
On wetlands nourishment. What's the impact of damming on wetlands nourishment?
Yeah, damming has been kind of overrated in terms of its impact. There's 33 dams on the Brazos River and its tributaries, so there's no doubt that we're damn crazy in this state. And there's no doubt that the Rio Grande situation has been impacted. I mean, I forget the name of the dam now. That's only 30 kilometers up the Rio Grande River, but it's had an impact. They've measured decreased sand transport. The Brazos, not so much, but what happened to the Brazos is they diverted it. The Corps of Engineers actually dug a new channel, and the Brazos River now empties into the Gulf of Mexico about 6 miles to the west of where it's supposed to be. As soon as they did that, the Brazos Delta just disappeared in 30 years. So if you want an example of how fast coasts respond, the Brazos River is a good one. Pretty big delta is gone in 30 years after they diverted the river. Once the river was diverted, there was a new dam formed by sand eroded from the old delta. And then for the last 30 or so years, that sand supply has been exhausted and the Brazos River delta is getting smaller. The Colorado River used to be a large delta that extended out into the continental shelf. It's now a bayhead delta. And they've tried on 1 or 2 occasions to dredge a channel where it can go out into the Gulf of Mexico, and that channel just fills in because there's not enough sand delivery from the Colorado River to maintain that channel. Certainly it's not nourishing Matagorda Peninsula, which is one of our 3 sort of dying barriers. So dams are a big problem, no question about it. They're not helping, but they're down on the scale 1 to 10, where there may be a 6 or a 7 compared to sea level, climate change, and some of these other factors. Yes.
So I have 2 related questions. And since we're handing this back and forth, I'll ask both of them at the same time. I'm going to go back to one of your first couple of slides. And on one of those, you showed sea level rise, and sea level was rising even before 1900. So my first question is, why was sea level rising, in the 1800s? And so that's just sort of the first question. I'll add to it, if this is a climate change anthropogenic problem. And then the second question, you showed the really high CO2 levels now compared to historical records, but sea level rise hasn't caught up at all. You said it just hadn't caught up. Is that, so it's sort of the devil's advocate position. What evidence is there that it really is going to catch up, that it's just lagging behind?
One thing I failed to mention here is most of these effects we're seeing, like sea level rise, are not reversible. So if somebody comes out, we read in the newspaper tomorrow that somebody's built this huge pump that'll pump carbon out of the atmosphere and get rid of all the excess carbon by the end of next week, it won't change a damn thing. And that's because when you start glaciers melting and the reversal for them to start actually moving back down valley, not up valley, or when you melt ice shells, and these are all things that are, you know, once perturbed, it takes centuries, most scientists believe, to reverse the process. So I guess that's more in line with your second question was, you know, how do we know that we're causing the problem? Again, I think the sea level record that you mentioned 200-300 years ago, it was still coming up, no doubt about it. It was coming up at about 0.5 millimeter per year. Today in the Gulf, it's coming up about 10 millimeters per year. That's a pretty significant influence. But again, go back to the argument about vertical accretion of wetlands. The kind of tipping point there is about 6 millimeters per year to 10. So it's that threshold that we've crossed that is causing wetlands to disappear at the rate they're disappearing at. Well, you know, we are still coming out of a glaciation, as we've seen. Theoretically, eventually in another 20,000 years, we'll probably be up to the Ingleside shoreline again. So there's pretty good evidence that it can get higher. And nobody knows when the Antarctic ice sheet's going to stop melting naturally, or when the Arctic ice sheet will stop melting naturally. So we don't know when that would happen if we were not involved. But what we do know is that the rates at which we're measuring Antarctic deglaciation, mountain glaciers deglaciating, all these things are happening at decadal timescales. And if you look at the geological timescales again, these things are happening at centuries to thousands of years, these same rates of change. So yeah, it's still changing, but it's changing a heck of a lot faster. So what we've done is to speed things up, and we've sped them up significantly. I mean, when I first started in this field, and my work started in Antarctica, and back then we used to say, well, the Antarctic ice sheet is stable, it'll never melt. And now I know nothing could be further from the truth. And, you know, climate change is a really complicated science because it's a domino kind of thing. If you look at, so, okay, we know that the Arctic's getting warmer. That's theory, 20 years old. People said the northern hemisphere of the Arctic is going to heat up faster. And that was the climate models, and that proved true. What we did not predict was that that would result in the sea ice around the Arctic disappearing 10 times faster in some cases than we thought it would. And we never thought it would affect the Antarctic, and now the Antarctic's starting to see rapid sea ice retreat. What happens when there's sea ice retreats? The ocean absorbs more energy from the sun. They get warmer. So then you get into this feedback loop, the ocean feeding the atmosphere and vice versa. As the atmosphere gets warmer, the jet stream starts to slow down. The jet stream slows down, it starts to get more sinuous. It dips way down into Texas. Next thing you know, you got these Arctic air masses that are coming down into Houston. and creating freezes that we haven't seen in historical time in this case. And these were not predicted as much as the science community would like to say, oh, we predicted that 20 years ago. We didn't. We weren't smart enough to know all the dominoes and, you know, how they would topple over and affect the next one. And now we're looking back, I'll admit, and saying, damn it, I never figured that. We didn't consider that in our models. In Antarctica, we never figured the rate of warm deep waters that are coming in and melting the ice sheet from underneath. The biggest threat to the glaciers melt rates in Antarctica. And until say 20 years ago, that was fine. We thought about it, but we couldn't measure it until 4 or 5 years ago. Sometimes even when you come up with ideas, it takes years for the technology to catch up and allow you to test those ideas. So climate modelers, we find ourselves apologizing a lot for things we were really not able to control. But so be it.
One last question from the audience.
Yes.
So your take on carbon sequestration, worth doing, or is it too little too late?
Absolutely worth doing. We have to find ways to reduce carbon in the atmosphere and carbon emissions. I didn't want to give the impression that we should stop that very important work. I'm simply saying that once we reach the point where we can start removing carbon from the atmosphere, that will slow down the rate of greenhouse warming. It ain't going to reverse it. So the damage that has been done in terms of the ice has been melted, the heating of the oceans, so let's say we immediately took the carbon out of the atmosphere. Given the rate at which the oceans mix, most oceanographers, climatologists would argue that it'll probably take 2 to 3 centuries to dissipate that heat. So to the point where sea level will start to go back down again. And for glaciers, it'll take longer. You know, when you go to Alaska and you see those glaciers that used to be out there in 200 meters of water, and now they're in, you know, up in the land as far as you can see, they're on the shore. If you start to cool things off, that glacier is not going to retreat back there into the ocean. It took a Pleistocene cooling to do that, to get them out there in the marine environment. It's not going to, you know, one or 2 degrees is not going to make a big difference. So you can't reverse those things. So I think we're going to have to get used to it and live. And I really don't like to hear people saying, well, I don't think we need to worry about it because I think we're going to get the carbon out of the atmosphere and that's going to solve our problems. I don't know too many scientists that would agree with that.
Thank you very much. A great talk.